All right, let's go ahead and get started. My name is Daniel Austin, and up here it says Interstellar Travel Inc. That's my little consulting company that I use when my employer does not want me to put their name on my slides because they're not sponsoring my activities. And I'm chief architect at PayPal. Before that, I was chief architect at Yahoo. Before that, I was a distinguished engineer, actually, at Sun. All these titles vary over the years as they've evolved. I've worked a number of different places in the Valley. I've done startups, I've done very large companies, and the one thing that I've spent my career on focusing on is performance and making the web faster and smarter. And when people ask me what I do, I tell them I'm on a mission to make the web faster and smarter. And this gets rid of a lot of the conversation about what is architecture and things like this that you get if you tell people, you know, oh, I'm an architect, right? And immediately they think that you're out there designing brick walls or something. Be that as it may, I work in the Valley, I work for a lot of these large companies, and Interstellar Travel Inc. is simply my consultancy that I use to give these talks. The goals of the class today. What do you want out of it? That's important. What I want for you is to give you a basic understanding of web performance so you can do something about it, right? The goal here is not to wax on about the theory of TCP and the congestion window and this sort of thing. It's not to tell you about, you know, server alternate name entries in your SSL certificates. These are all great issues. But given that we only have 8 hours today, what we really want is to get a solid, basic understanding of how the web works from a performance point of view, how to identify what your problems are, if you have any, your opportunities for optimization, what can you do to make things faster. Along the way, I'm going to demonstrate and explain some of the tools. That's always very important. This whole field is just riddled with tools. It's part of the problem is not that there aren't enough tools, but there's far too many, and what they tell you is often ambiguous or misinterpreted. A little bit of self-serving promotion here. This class is based around my upcoming book from O'Reilly. And going to be out on October 25th. It's you can pre-order it on Amazon today. Yes, everybody smile. Pre-order. No, I'm just kidding. That's all for the self-serving promotion. But I just wanted to explain how the situation with the book works here. This book is already in the pipeline. It's half written. We've got a rough cuts coming out. Immediately following this book, I'll be publishing an additional book called, and the title is not really very catchy, I'm sorry, The Definitive Guide to Web Performance. And it's intended basically as this is the getting started class, this is the book that's about the material that's in this class. The next book goes into a lot more detail about technical issues that I don't have room for in a getting started book. So I encourage you all to buy it. Of course, you're here today. You're going to hear most of the material in there anyway, so you can make your decision, but it's going to be good. And that's enough for the self-serving promotion. So, scope. What is web performance? What's in, what's out? We can't talk about everything. I can't stand here and tell you how to optimize your Oracle queries, how to optimize your Apache config. I can't make your applications run faster on the application side. We're focusing on anything that uses the HTTP protocol, anything that's addressed with a URI, right? We're going to talk about performance from the user's point of view. This is called the user narrative. We're not going to talk about this from the point of view of the server or from intermediate. We care about the user. Some poor soul out there with a mouse or a mobile phone in their hand is suffering, or not, from your pages. And that's the person we're going to focus on. And we're really just going to focus on the request response cycle and avoid a lot of the complexities around, say, streaming video and some of these things. Not because they're not interesting topics or worthwhile, but we only have limited time. Where are we now with web performance? Well, it's getting a lot better. When I first became chief performance architect at Yahoo, there was one guy, really, who was spending a lot of his time on it, and he went to Google. He's actually speaking tomorrow. His name's Steve Souders. But there really weren't that many people working on this stuff at this point in time. I had worked at Sun, built a very large monitoring system, spent a lot of time on performance, and was very disappointed in the state of the art, the state of the industry, the thinking that people were doing, and maybe more importantly, were not doing. But things have gotten a lot better. I like to say that it's an art and a science in the rhetorical sense, in that there's an art, there's something to do, and a science, something to be learned. Anybody who remembers their rhetoric class will remember this if you studied the trivium. There's all kinds of tools. Like I said, we are overwhelmed with the number of tools, and it's very difficult if you don't already have a solid background in this stuff to even figure out which tool is the right tool to use. When your tool doesn't tell you what you thought it was going to tell you, you tend to be frustrated, you tend to move on past that problem. One of the things I want to do is sort of disentangle the tools space a little bit today, see if I can give you some pointers on how to pick the right tool. Obviously, like I said, things are getting better. The W3C has become involved. There's a web performance group at W3C now. I'm actually a member of that, disclaimer. And we published some specs. We'll talk about the W3C navigation and resource timing specs a little later, and how you can hook those up and see what's actually happening to your users. The last thing I guess I want to say is that there's hope. It's not going to be permanently a backwater or an unregarded part of the profession. So this slide changed a lot from last year. Last year I only had like 2 or 3 books that were really available here. I've added a couple, some based on my own reading and thinking and understanding, and some that have just come out in the meantime. Ilya Grigoryk's book on browser networking. If you want to really know what your browser does, go get Ilya's book. He's an expert on this. He doesn't talk about performance as a focal point. He's talking about how the networking works, but he does touch on performance. A lot of the material that I cover in my book and in here is also given a lot of background and support by Ilya's book. Obviously, Steve's book is famous. Go get this. This monitoring and alerting book is really useful in a number of different ways. I was searching for references when I was writing my own book. I didn't want to write stuff down that somebody had already written down, so I was trying to find out what was out there and what was available for people to read. I stumbled across this book. It's the only one that talks about operational research in an operational quote sense that I've been able to find. Only person that talks about the response time law anywhere in any book. Very interesting how little information there is. This book on systems performance takes a much larger global view of things, talks about a lot of things that aren't on the web. It's very useful, but it's a textbook. You'll get what you get out of textbooks from it. The interesting book that I wanted to point out here that I think is well worth reading is this book on engineering psychology, and they say human performance. And when I first read that, I thought it was very interesting because it sort of coincides with an insight that I had a long time ago that I think a lot of people don't think about in terms of web performance, which is that what you really have here is a conversation between a server and a person, not a browser. We talk about the browser all the time, but the end consumer of that information is not the browser. The browser doesn't care what came back in your Google search, right? The end consumer is you, and you're connected to that system via an optical link, right? It has about 16 megabits of bandwidth between the screen and your eyeballs. Right, that figure came out of that book, actually. And this book talks a lot about a lot of interesting things about human psychology related to performance. For instance, I wasn't aware, I'm not a real movie fan, I wasn't aware that movies are shot so that there's about 300 milliseconds of still frame in the movie so that your eyes can perceive all the large objects in the room. After 300 milliseconds, you've got the room fixed, then they have the little conversation and do this. And this is everywhere in movies. It's a standard, 300 milliseconds for people to visually grasp the field of view. If you think about how that plays into web pages, we have to ask ourselves, okay, so we can continue to make web pages faster and faster. We can change HTTP. We can, move your house on top of the data center. We can do 90 different things to make your web page faster. How fast is fast enough? Right? I mean, sure, we can build nuclear power plants and all kinds of things. There's a limit to how fast things need to be. Nobody ever complains about television. Have you ever heard about anybody say, oh, television's really slow? Right? I mean, it's kind of funny, right? It's like the idea just doesn't sound right, does it? But we all the time complain about the web being slow. I mean, come on, it comes into your house over the same wire now, right? I mean, obviously, there's a difference there. TV is fast enough. The web is not. How do we determine when the web is fast enough? And I think the key to that is in engineering psychology. In my book, I say, your page is fast enough when the user is not at all concerned about the speed of the page and can interact with it as if it was instantaneous. That doesn't mean it's instantaneous, right? There's a lot of time involved in the things that we do, hundreds of milliseconds. But if the speed is not an issue for you, if it loads as fast as you expect it to load, that's probably fast enough, right? And additional optimizations may cost you more money and turn out, is it really worth it to get that last 3%? These are choices you have to make, and kind of guiding you on how to make those choices is part of our talk today. Yes, sir?
That experience has changed clearly over time. 10, 15 years ago, our expectation of speed is different than it is today.
Right. Users want more now, right? Yeah.
Dial-up and so on, right? While page load times have decreased in speed because of the technology available to us. So our expectation is relatively dependent on the technology.
And just like you're saying, as things have gotten better, the users' expectations have risen, right? When we all first started surfing on our phones, we were just shocked at how slow and 14.4 it felt to us after being on our LAN or WAN connections, right? And I still get that experience. I'm like, oh, this could be so much faster. Fast enough really means your user is never concerned about performance. And beyond that, and this is a key point that I want to make and sort of ties into what you were saying as well, we don't often think about how reliability affects people's perceptions of performance. But let me give you a scenario. I used to give talks at Yahoo and I talked about this. If I get up in the morning and I stumble into the kitchen and I make my coffee and I wander into front of the computer and I go to Yahoo Mail because I'm going to check my mail, I have a very good expectation of how long it takes Yahoo Mail to serve it up and log in and bring my mails up, and I know what it does, right? I have an expectation about its performance. The next day I go and do the same thing, and for whatever reason it's really slow. Right? Maybe it's only 20%, 30% slower than it normally is, but because my expectations have been set by reliable performance in the past, that unreliability of the performance is a huge jarring experience. It's like, damn, Yahoo is slow this morning, where in the hell is my email? And that gives us a key into the nature of people's thinking about performance. It's not just what the response time is in that spot measurement that you made on that Yahoo Mail page. It's what does the user expect day in, day out for you to do? And if you don't do it, they are more disappointed than if you were unreliable and half broken all the time. This is sort of a difficult point for people to understand, but there's a second order expectation that users have that not only is it fast, it will continue to be fast. And when it fails, they're vastly disappointed. So those are some of the sorts of insights that I was able to get from this book and some other books on engineering psychology. There's a lot more. Let's see, tools for the class. I think I asked everybody, but let me just make sure everybody has some Excel-like substance. Access to being able to manipulate more than 4 or 5 numbers at once. Stick your hand up now. If you don't have it. Okay. Online testing tools, we're going to use webpagetest.org and speed test. These are both free. If you can get to the internet, you'll be fine. That's actually what we're going to test, isn't it? How well you can get to the internet and how good a connection you get once you get there. There's some desktop testing tools. I'm assuming everybody has a browser. Please don't raise your hand if you don't. I'll be so disappointed. The Firebug is good if you use Firefox. It's bouncing around between version compatibility right now. I'm not sure if Firebug is actually available for the current versions of Firefox. I should have looked at that. I'm assuming that everybody has access to a command line of some sort, right? Whether it's either the Windows command line or the Mac command line, you're going to need to be able to type things like dig, ping, and curl. All of those are present native in the Windows system. You don't have to download Cygwin or anything like that. The names of the commands are different. Traceroute is TR and so forth. But you need to be able to get to those tools, especially curl. Does anybody not have curl? All right, so can you get curl? All right, thank you. And then there's some mobile tests, and I talked about those earlier. If you can, try and download some of these apps onto your smartphone. And most of them should be available for both major smartphone vendors. So Speed Test app, this is very similar to this speedtest.net, made by the same people. HTTP Watch Basic, only available for the iPhone, but it's the only tool here where that's the case. This is actually the #1 best tool for spot testing and diagnostics for web performance on mobile. The net tools, these are the things that I've talked about here. You also need them for your mobile device: dig, trace, ping, curl. If you can, try and get some of these things onto your phone before we get to that part of the talk, just so that we're ready to go and we don't have to spend too much time fumbling. There will be breaks and so forth. Speaking of breaks, let's talk a little bit about the structure here. So we started at 9, very good. We started on time. We're going to have a break at 10:30, lunch at 12:30, another break at 2:30. We'll end at 4. 4 is the canonical closing time for this class, but I found that no matter what I do, it seems like I always run over. So if I do run over, I will stand here and finish until I'm done. You're free to leave at any time, not necessarily at 4. I'll also stay after the class and answer questions and just talk if people want to talk. They often do. First section, what is performance? Nice numbering there, Daniel. The performance basics, the MPPC model, that's multiple parallel persistent connections. If you don't take anything else out of this room, remember, multiple parallel persistent connections. That's how the web works today. Tools and testing, HTML5 in performance. Disclaimer, I've been a member of the HTML working group at W3C since 1996, and am the longest serving member of that working group. So we're going to talk a lot about HTML5 because it's near and dear to my heart. And like I said, there's mobile devices as well. And we're going to cover those in more detail this year than we did last year, obviously. You know, we're going up the mobile curve here. So the other thing that I want to note is that between every section, you'll find a nice, relaxing picture of Mount Fuji. And the pictures of Mount Fuji are here to calm you down between each section, give you a little serenity, tranquility as we go into the next section, and also just because I really like Mount Fuji. Yes, sir?
I was just wondering if your slides are going to be available later.
Minus the pictures of Mount Fuji, yes. No. Actually, the slides, and I should have said that earlier, the slides will be available on SlideShare at the end of the day today. And I don't release them before the class. But otherwise, they're out there, and the slides from last year are out there as well. If you want to do a diff, you can see what I changed. I'm not sure if you can do a diff on PowerPoints. Somebody should write that, huh? Anyway, so what is performance? What problem are we trying to solve by getting up early and driving into the city, struggling to find a place to park, and sitting here in this classroom? We want world-class response times compared to our competitors. That does not mean that you're going to be faster than they are. If you're Google's competitor, you're going to struggle to make your pages faster than they are. That's not a criticism of you or your performance work. You might very well be in a different business. And they're crazy optimizers anyway. You're going to have to work really hard to do that. World-class performance doesn't mean that you have the best performance, that you show up #1 in some ranking, whatever that ranking might be, and these rankings are a little bit touchy, right? I mean, if you think about it, how to compare these numbers is often not obvious. World-class means you have no problems. Any problem that you have, any error, anything that you could address has been addressed, right? World-class means that you have attempted to find the opportunities for optimization. You've taken advantage of as many of them as make sense commercially for your point of view, right? It may not make sense to reduce your response time yet another 10 milliseconds if it requires a $10 million investment. That's a decision for you to make. But world-class means as best as it can possibly be within the constraints of your business, your location, and your business goals. It doesn't mean being the fastest. I can't stand up here and tell you that I'm going to teach you how to make your website the fastest, because your competitor is sitting right there next to you and he's going to be working on it as well. Reliable and predictable performance. That's what I was talking about earlier. It's not enough for your page to be fast. It has to be consistently fast so that you can set users' expectations, so that you can keep that promise, that implicit promise you've made to the user. Yes, user, it will be as fast or faster tomorrow than it is today. Reliable and predictable. If you're a business and looking at this from the other end, obviously you want things to be reliable and predictable for cost and efficiency purposes, right? Reliable and predictable is a sign of a healthy system. Efficient use of resources. This doesn't mean that you can do everything on the cheap. I know a lot of companies, especially at startups, are really tempted to do everything in this very cheap way. And being lean, I was just reading in a book, doesn't mean being cheap. Right? So when we say that we're going to make efficient use of resources, that doesn't mean we're going to cut the budget 10% this year. It doesn't mean, oh, we're going to save a lot of money on hardware and equipment and we can take that money and give it to marketing. What it means is that our cost scales linearly with the traffic. As we get more users coming in, our costs go up, and they go up in some relatively linear way. Right? It doesn't go exponential when that 1,001st user shows up at the door. Right? That's what efficiency really means, linear scaling. So that's our problem. How do we do it? How do we make sure that every user, mobile phone, mouse in hand, gets reliable, predictable performance at a linearly scaling cost and doesn't encounter any problems or optimization opportunities that have been left alone? Everybody has a slide like this in their talk, and I've seen dozens of these. People will come out, Google, Amazon, Yahoo, they'll come out and say, oh, if you reduce your response time by so many milliseconds, it'll increase your traffic, reduce cavities, cure cancer, all kinds of things, right? So of course I have to have one of these slides as well. But this is definitely a grain of salt slide. Right? Your business cannot take any valid inference from Google saying that, a reduction in 500 milliseconds reduces traffic to sites by 20%. You can't infer anything like that. You may very well be running Etsy, where the whole page is full of thumbnails, and it takes each individual thumbnail 500 milliseconds to load. They're just not in the same business that Google's in. What sort of inference can you draw? The only valid thinking that you can do when you look at these numbers is to say, some people have found that when we improve performance, traffic gets better, revenue gets better, conversion rates increase. That's all you can really say. Improving performance makes things better. If you want a real cost or quantitative measurement, you're going to have to do some analysis on your own business. You can't take what Google or Amazon say and apply it to your business, or take that into your boss and say, look, Amazon says if I reduce this 100 milliseconds, our revenue is going to increase. Right? Not a valid inference. On the other hand, I think that every one of us as users, let's put on our user's hat for a minute, right, knows that when we encounter a slow site, what do? Right? We get the hell out of there. Right? We try to find something else, and we try to think of alternatives. Oh, Amazon is slow. I wonder if drugstore.com is up. Right? Maybe they can do a better job. Netflix is slow. I wonder if Amazon Video might be a little bit faster. Right? We think that all the time. Performance has a huge impact on the business. Reliability, predictability has a huge impact on the business. So when I used to work at Yahoo, I worked for this guy named Philo. He was one of the founders of the company. And he's sort of a character in his own right. And he never wanted to be thought of as a boss or supervisor or anything like this. Was not, that wasn't his style. So I put together this slide showing him as the pointy-haired boss in Dilbert. Right? Specifically just to see what he would say. He didn't speak to me for a week. But I wanted to put this question up here because I get this a lot. It's like, okay, so you can make a DNS work a little faster. You can reduce the number of connections on our webpage. Who cares? Does it matter? I mean, shouldn't you be out there, in marketing, pushing ads, or and ads never made anything faster. Underline that. right? Shouldn't you be doing something else? Why do we care, right? Who in this organization really cares about this other than you, Daniel? And you're obsessive about it, sitting there watching your phone and looking at your bandwidth and staring at those funny waterfall diagrams. Who cares, right? Why should we pay you for your obsession? Well, I hear this a lot. Actually, I really do. It's kind of embarrassing. When I first started answering that question, I basically said, you do. You need this. And here's why. But that wasn't really a very convincing answer because it sounded ad hoc and like something I was just responding to somebody challenging me. So I decided to take a more rational approach. Rational being quite literally, I made a use case diagram. Right? So I'm not going to show you all the use cases here. This is just an actor and use case catalog for this. But I wanted to give you an idea of what the use cases are for performance. And some of them might surprise you. So let me just see here. I'm having trouble reading my own slides a little bit, right? So as far as who cares, right? Obviously the engineering staff, the management staff. What about the business continuity planning staff? Those folks that are back there to make sure the lights stay on no matter what. They care, don't they? Right? The capacity planning staff. Performance and capacity planning are two sides of the same coin. If you don't do good capacity planning, your performance is going to be miserable no matter what else you do. Those people really care. The systems engineers, the network operations staff, the people who do performance for a living. Right? There's companies, most of them have, site reliability engineering, site integrity, exceptional performance. All these companies have these different groups. Your third-party business partners sure care. I work for PayPal. Most of our discussion is between some merchant and ourselves, right? We have arrangements with these third-party merchants in some cases. Some people just come and download our SDK and, hook it up. It's not so hard. But we have arrangements with these other people, and very often they have SLAs. It will load in 600 milliseconds, or we're going to come knock on your door, right? Your third-party business partners really care about your performance. User experience designers, front-end engineers. Out of all these people, is there somebody I left out? Who are we here for?
End customer.
What?
End client customer.
Yes, the user. The user is not up here because he doesn't really play a role in these use cases. But I always try to keep him in mind because he's the person we're here for. I'm not here for the BG people or the front-end engineers. They have lives of their own. It's the end users with a mouse in their hand. When we look at some of the use cases we want to match these actors up to, resource planning, monitoring and improvement, resource planning at the lower levels, platform dependency management. Oracle depends on the middleware, depends on the web servers, web design, capacity management, real-time support and notification. If the site is running slow, boy, there's a use case there for those people who are sitting there doing customer support and listening to the phone, listening to the user run on. Right? All of these things, contractual SLAs, failover and recovery, support and diagnostics, all of these are very, very typical use cases. These are not necessarily big company use cases. These are medium-sized company and large company use cases. It may very well be that if you work for a startup or a very small company that most of these use cases are either conflated, most of the actors are certainly conflated. Every one of the concerns addressed by these use cases is encountered by everybody that runs a website. And so that's who cares. We're going to start now on the next section of this, and what I'm going to try and do is put performance in perspective as a systemic quality. So, we're all performance people, right? We want it to go fast, but performance is not everything. It's not the life, the universe, and everything. There's a lot of times where we have to look at the qualities of the system and make trade-offs. At PayPal, where I work, we make trade-offs all the time between security and performance. Guess which side we come down on? It's not the performance side, right? We always come down on security when we have to make those sort of trade-offs. But that isn't necessarily always the right answer either, right? It would be nice to say, oh, we have a policy. We always go for security when we have to do a trade-off of security and performance. But that's not the right answer either. The right answer is wisdom, judgment, experience. Don't make hard rules. But the next section here, I want to give you an idea of where performance fits in. So we're going to talk about the systemic qualities. Sometimes you hear people say ilities. One thing I really hate when I hear is people will say non-functional requirements. And it's like anything that's non-functional, it's okay, I'm not going to work on it. The system qualities sort of correspond to different groups of users in the system. This all comes out of a sort of well-developed theory of architecture called the Suntone architecture methodology, and I actually wrote this section of Suntone. The systemic qualities are anything you can say about a black box from the outside, right? So think about Oracle, right? It's like you may know how Oracle works internally. It's got a query cache, and it's got a data cache, and it's got all kinds of different mechanisms internally, but you don't care. To you, it's a black box. You send some SQL in, result set comes out, it's all you care about, right? From the user's point of view, that's what the web looks like, right? They click on something, something comes back. It's a black box. It's a system, and we want to talk about its systemic qualities, right? Not the internals. There's 4 classes of systemic qualities. The manifest ones are the ones that we're talking about today. These are the ones that are apparent to the user. Right? Manifest to the user, usability, performance, reliability, availability, those 2 things are very different. Accessibility as well. Operational qualities, these are things that the sysops care about, that no user really cares about unless it actually has some upstream impact on the manifest qualities. But these are things like throughput, manageability, security, serviceability. The developmental qualities, things that developers care about. Can we build this? Can we plan it? Can we maintain it? Can we update it? I worked on an automotive project recently where I was trying to build an app for a car, only to discover 2/3 of the way through the project that there was no possibility of updating it without bringing the car to the shop. Yeah, that project didn't work very well, right? Buildability, planability, these are really important things. That project was not my idea, by the way. The evolutionary qualities, these are the things that everybody who has a stake in the system cares about. Not just the operators, not just the people who pay for it, not just the end users, but everybody. Scalability, maintainability, extensibility. Can we make this thing future-proof? Reusability, those 2 things are different. Portability, and that's, once again, different from these 2, right? I'm trying to give you an idea of the different kinds of systemic qualities that we can look at and who's concerned with which ones. For our purposes, we care about the manifest qualities because we're doing everything from the user's point of view. Manifest qualities, usability, how easy it is for users to do things. Performance, this one always sort of gets people's eyes a little wide on the screen. They're going, oh, that's how he defines performance. Almost, right? How little time it takes for users' actions to complete, right? Nothing there about packets, right? Nothing there about frames, right? Performance is response time. Reliability, how often does it fail? Availability is uptime versus downtime. That's different from system failure. There's lots of failure modes that don't have anything to do with being down. The accessibility, of course, and accessibility actually has a little bit different definition sometimes than I think that people think it does. They often think about it in terms of, the physical condition of the users because that's often the context that we hear it in. But that's not really the case, right? There's localization and internationalization, which are accessibility issues, right? There's pure bandwidth issues. If you're in, Burkina Faso, right? Accessibility has a much larger meaning than just talking about people who have significant physical handicaps, right? Accessibility means that we keep the promise that we made when we called it the World Wide Web and said it was for everybody. Like I said, performance involves trade-offs. It's not always the case that you want to optimize for performance. That's actually an anti-pattern, keyhole optimization. We'll talk about that in a little bit. Security versus performance is a common one. Obviously, it's going to be near the top of my mind, given where I work and what I do. But there's also a lot of other trade-offs, right? We can make it faster if we build it using specific code that's native to this platform, but that's not very portable. might not be very extensible. But we hear that a lot from the app people, right? It's like, oh, I'm going to build it for the iPhone because damn, it's going to be fast. And it's like, okay, so that might be a good decision for you. I don't understand your business. I don't know if that's a great decision, but it sure as hell isn't portable. You actually just made a trade-off between performance and portability, right? Those trade-offs occur everywhere. Architecture is nothing more than deciding which trade-offs to make and why. That's all it is. And gaining the wisdom and experience and judgment to make those trade-offs and make the right one is really the high-level skill in this business. You heard me say this before, so I'm not going to repeat it. Maybe I should actually get you to repeat it. Performance is response time. Performance is response time, right? I repeat it and emphasize it so much simply because I hear so many people say latency, 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 latency. It's not about latency, it's about response time. How many packets do you know personally? Yeah, but you know a lot of web pages personally, right? And it's how long they take to respond to you that really matters. How little time it takes to accomplish your task. That's how we define performance. All right, so Section 1, we're back to another nice view of Mount Fuji here. I tried to progress through the seasons a little bit with Mount Fuji, and so it's getting a little bit into summer now from springtime. What's performance? What? All right, thank you. Does anybody disagree with that position? Somebody want to defend the idea that performance is latency or it's bandwidth maybe or something else? I mean, I've had people pop up in class and say, look, it's about network latency. And that's okay. I'm perfectly happy. I'm not always right, for one thing. And the other thing is that when people challenge your ideas and you have that discussion with them, they're often much more convinced than if you just stand up in front of them, right? And reel it out. So feel free to challenge me on any of this stuff. But I did want to get that idea that performance is response time into your head because you're going to hear so many countervailing opinions. All right, so performance basics. This part is where we get into the boot camp part. Hopefully you've had your Red Bull. Yes, sir.
Isn't the performance of JavaScript much faster than the performance of the network? So effectively, latency and response time are the same because JavaScript is so much faster than the network.
Okay, so the question was, just so everybody can hear it, the gentleman's saying that because JavaScript executes more quickly than the average network transport times, is it not true that the actual performance is pretty close to the response time? And is that, or the latency, I'm sorry. So what do we think about that? So here we have a web page. It's going to run some JavaScript. We got to get it down to the user's client, and then the client's going to execute that JavaScript somehow, and there will be some result. We don't really care what it is, right? So we're going to go through exactly how to analyze that, and you'll see why you're not quite right in just a minute. But here's a way to think about it. I have to make a connection, right? I have to send that data down. The browser has to read it, then execute it and do whatever it does. My claim is that those first three segments, connecting, making the request, sending that response down, easily overwhelm the execution times on most devices. Now there's probably some exceptions to that. JavaScript runs much more slowly on mobile devices, and some mobile devices are actually worse. But as we go through this, you'll see, I think, that what you're saying is not quite right. There's a lot of time in the E2E that is not related to the network latency. So let's see, hold that thought for a minute, because you're not convinced, and that's okay. I can see on your face you're not convinced, and that's fine. I'm here to convince you or not. But hold that thought for a minute, because we've got to do a little bit of statistics. This is the boot camp section, and everybody's had their Red Bull, right? Because I'm going to march through this. So when your boss says, go make that website faster, what do you say? You say, oh, here, let me look on LinkedIn for another job. Right, no, what do you say?
Start measuring it.
No, before you get to there, so you're going to have to do that at some point, but what do you say? It's like, make that website faster. What do you say?
I ask them what they perceive to be that needs performance numbers.
Right, so that's the right answer. I mean, obviously you're being very nice and polite and courteous about it, right? The real answer is faster than what? Right? Fast is relative. You want to make it faster than Google? Fine, you got a geothermal power plant? Let's hook it up, right? Faster than what? I get that a lot. Go make that website faster. Can you make India faster? I get this one a lot. It's like, can you make India faster? And I'm like, well, let's see. It's a tectonic plate with some dirt on top of it. I don't think so, right? When people talk about performance, they need to use a little bit of precision in their language, and this is sort of how we get started with that, by understanding the way that we measure things and the scales we use. There's really 4 of these, and I'm not going to belabor this, right? There's a nominal scale, and the nominal scale is good, better, best. You give it some categories, you give them names, you don't specify what the relationships are between them necessarily, and you just put things into buckets. This is pretty much useless, right, for most purposes. There's ordinal scales where you have, identifiers, then you might have an order to them. Good, better, best actually has an order. I think we could assume that, better is better than worse, right? So that's an ordinal scale. It has order. Now, if I have a scale that has 1, 2, 3, 4, 5, and I say, okay, on a rank out of between 1 and 5, how fast is this website? And you say 4, or 2, or more likely 1 if you're on your mobile phone, right? That's an interval scale, right? The differences between the measurements are happen at some fixed interval, and you can do some math and a little bit of thinking and inference on that. And then we have ratio scales. These are the full-blown scales where we have rational numbers and we can divide and do everything that we want. When we measure performance, nominal scales are useless. Ordinal scales are what you get when your boss says, oh, go make it faster, right? That's not helpful. Faster than what? How much faster? Faster where? On which device? For which user doing what task? It's much more complicated than make it faster. So just briefly to go through the statistics part, we've got these 4 scales. If you're going to measure performance, which one do you want to use if you have your druthers? You always want to use some rational scale, right? It gives you the most power over the numbers. Yes, it's that slide. So I'm just going to calmly let you breathe in a little bit while you look at the slide. Calm down a little bit. I know your heart started racing when you saw the equations. More seriously, this is all the statistics you're ever going to need to know, pretty much, to do performance. And you should have already had it. This is just actually a cheat sheet that I stole off the web from somebody for their Statistics 101 class. These are just concepts you should be familiar with. I'm not going to define them or belabor them. If you don't know these things, go brush up, right? Mean, median, mode, variance, standard deviation, coefficient of variation, min, max, and range. We're going to hit all of those in about the next 20 minutes, I think. But is there anybody in here who just finds this totally mystifying? Not the funny Greek letters, but the ideas. Everybody's had some basic statistics. Good. I hate going over this stuff, especially when somebody pops up and says, what's the mean? And I really want to get people to have some basic understanding so I don't have to go over it, because none of us really love this stuff or want to belabor it. So we're going to start talking about the mean, the median, and the mode. We don't care about the mode. Forget it. Ignore it. Right? We do care about the mean and the median, and we care a lot. Right? Because these are the 2 characteristics of our samples, and when we measure stuff, we're taking a bunch of samples, right? The mean and the median are 2 primary characteristics or central tendencies for this distribution. There's a lot of argument and controversy. Should we use the mean? Should we use the median? Under what circumstances? One of the deceptive things I find often in performance practice is I'll go into a meeting and somebody will show me some numbers, performance numbers, and I'm like, oh, that looks interesting, that looks good. And then they turn around and say, oh, those were means, those weren't medians. And I immediately know that my conception of that data was incorrect. The mean and the median produce very different values for the distributions that we typically see in performance work. Why that's the case is the topic for that definitive guidebook, not necessarily the getting started book, but it's definitely the case. What we see is a lot of stochastic outliers. We see a lot of values that distort these distributions, and when we actually go through and look at these things and I'm not going to belabor the math again on this, right? There's the definitions here. I think everybody kind of understands them. Like I said, you can ignore the mode. What we do find is that we can't use the mean for much of anything. So we use the median because our distributions are normally highly skewed. Now you can see here's some just sample distributions. These are actually real distributions, by the way. This is just for a single object on a page, so it comes out in this nice Gaussian way. These are actually for web pages. So if you were going to guess, we all know what histograms are, right? Hope so, right? If you were going to guess which distribution looks like the web, if I'm going to go take a performance, let's say I take 100 tests of Google's response time, what's the curve going to look like? What's the distribution going to look like?
Guess A.
Anybody else got any other ideas? Yeah, no, I mean, that's right. It's going to be, I mean, nothing is perfect, right? And obviously, the Gaussian does not work. We can't imagine it being skewed to the left. If this is your distribution from your web page, boy, you have real problems, don't you? Right? It's like the majority of the users get slow response times, right? They're way out here at the end. Unfortunately, I suppose there's probably a lot of sites where this is the matching distribution, and you want to get it to be that. Maybe that's the fundamental action of performance science, is to change the distribution a little bit. Be that as it may, what we typically see are these heavily skewed distributions to the left and a long tail of outliers in the performance space. This prevents us from using the mean effectively. And you can sort of see here that in that first data set that this gentleman picked, the mean was about 2.64 and the median was 2. Very different, right? Remember, our range here is only 6, right? For the skewed distribution over to the right, same sort of thing. Obviously, for the normally distributed pretty distribution, the mean and the median are okay. For performance work, don't use the mean for anything. There's no real purpose for it. It's not robust enough in the face of outliers to serve as a true measure of the central tendency of your distribution. Now, there's a lot of more work we can talk about, outliers, we can talk about quartiles and so forth. I'm not going to belabor the outlier issue. I actually have a blog post out there on what causes the outliers and the bimodal distributions that we see because of that. It's pretty technical. I don't think that you want to hear it at 9:30 or 10 in the morning. Anyway, stick with me. Use the median instead of the mean unless there's absolutely no way to do that. And be really honest about this. When you stand up and tell people about the data, tell them it's the median. Tell them it's the mean, so that they know and don't make assumptions. All right, statistical distributions. There's just a few questions that we want to ask about this. Are they discrete or continuous? What do we think on the web? Discrete or continuous distributions? Our samples are discrete, right? They can only take on integer values of milliseconds. The mean, the median, and the standard deviation, sigma, the 95th percentile. A little bit of a math trick here. The 95th percentile and the 2 sigma point, basically the same. The 2 sigma point's actually at about 96.44%. But if you want to calculate the 95th quickly for a distribution of numbers, and you know the standard deviation, it's just around 2 sigma. Is the distribution reasonable? People don't often ask this question when they look at a bunch of numbers. I'm often surprised they look at the standard deviation and they do the 5-number report and they don't ask themselves, does that actually look reasonable? Does Twitter's response time actually look like that, or is that crazy? So I've got some examples over here of some distribution. These are all the PayPal home pages in various places. And you can see here we've got Asia, EU, global. Global is everything that's not in Asia, the EU, or the US. Don't ask about the terminology. And then, of course, we've got it in the US. So the distribution here in the US looks, fairly reasonable. Here's our outliers. This is why we're not eligible for using the mean. Right, but what about that top distribution, or that second one for the EU homepage? Does that look reasonable? I mean, that looks like a seriously bimodal distribution with a huge peak where I don't even see any data. That doesn't look like a very reasonable distribution, does it? I kind of stuck it in here just because it doesn't look reasonable, and I kind of wanted you guys to see one thing that should trigger in your head just intuitively. It's like, WTF, what's that, right? So another way of testing whether numbers are reasonable, very simple. Chebyshev's theorem. Yes, it's a little bit more math, but it's very easy, right? If the difference between the mean and the median for your distribution is greater than a standard deviation, you're hosed, right? Seriously, there's no distribution with finite variance that has that. It's a very simple proof. You can go and look it up on Wikipedia and look for the Chebyshev theorem. And basically, the difference between the mean and the median can't be more than a single standard deviation for any data set with finite variance. That's us. Right? So very easy. When I see people popping up numbers, I sometimes will calculate this. And if I have some reason, oh, that's not reasonable, that looks funny, you know, I'm not sure about those numbers, I'll go calculate the difference in the mean and the median. If it's greater than 1 sigma, flush. It's a fail. Right? What it means is your tool failed somewhere, your data collection mechanism was unsound. Right? No sound data set ever does that. The other thing is, does it correlate? Right? And that's the question that you want to ask maybe about that second graph. That big peak there doesn't seem to correlate to much of anything in the data world, does it? Right? When you're looking at these distributions, and you're going to have to look at these distributions, ask yourself these questions. Is it reasonable? Does it make sense? Is that you know, so wildly different from what I expected the data to look like that it's worth further investigation? The margin of error. So nobody talked about this until I actually started working on performance at Yahoo. I'd never heard anybody talk about the margin of error, and I spent a year or so getting it into some executive heads what the actual margin of error meant. And the way that I did it was I collected newspaper articles, right, where they go out and they poll people and they say, oh, you hate the Democrats by a margin of, you know, plus or minus 5%, or you hate the Republicans plus or minus 5%. And I used that example to sort of explain what the margin of error was to people who weren't accustomed to dealing with numbers and mathematics. I'd like to actually use a little more rational explanation for it with you guys. I think that, you know, you've all seen those newspaper articles, you know, plus or minus this or that. Where do they get those numbers? What does it mean? So the margin of error, measure of how much confidence we have that the numbers that we put out there are actually close to being true. We know that when we take a bunch of samples, it's approximation, right? The real number may be 1.234567, and we measured it and we got 1.3, right? The margin of error is a means of looking at the data and determining whether we believe it or not. If I have a bunch of data and the margin of error is, you know, plus or minus 50%, right? I'm not going to pay too much attention, right? I mean, it's not much better than random, right? If I see something that has a 3% margin of error, that's pretty good, right? I'm 7% confidence that my number lies within a range that I specified, plus or minus 5%, right? Very carefully listen to how I phrase that. You can confuse yourself here. It's not a measurement of the accuracy of the data. It's a measurement of your confidence in the accuracy of the data based on what you know about the data set, right? And the whole purpose of doing this calculation is to look at that number and say, how confident can I be that I'm not full of shit? Right? And it's actually pretty easy. The fundamental issue that comes up in the margin of error, very simple, number of samples. It's all about the number of samples. You take more data, the data gets better. This is just the law of large numbers, you know, written out. So let's have a look at it here, right? So if we have a sample size of 96 items, and these numbers are fixed, right? It's not that if I choose a sample with 1 billion items that number goes to 9,600 or something. Anytime I have a sample of 96 samples, I can get a margin of error within 10%. That's pretty good. You know, if I'm out on a boat, if I'm one of those guys that drives Oracle's boat, yacht out there, then plus or minus 10% is probably good enough, right? If I'm Google and I'm trying to beat the hell out of somebody else with my web pages, 10% isn't nearly good enough. I need a lot more data. So to do that, I increase my sample size to 384 data points. Now I'm down to 5%. I did not make these numbers up. I stole this picture directly from Wikipedia. If you go to the margin of error page on Wikipedia, all I did is summarize it, right? Sample size 600, margin of error goes down to 4%. Now notice that when we went from a sample size of 96 to 384, our margin of error dropped by half. That's pretty good. But when we went from 384 to 600, it only dropped by 1%. So it looks like we're starting to see the point of diminishing returns here, right? At some point, we're going to have gathered so much data that there's not much point in gathering anymore, right? Wonder where that point is. Let's look. So if we increase our sample size by another 400 data points to 1,067, that's what it takes to get us to the 3%. To get to 2% margin of error, we need 2,400 data points, but that's all we need, right? And if I gather 5,000 data points, my margin of error is not going to go down much from this point, right? You only need to gather so much data, but you have to gather that much. And understanding the basic ideas behind this curve, right? So with a lot of samples, that curve is very narrow, right? My confidence about the value of the data is pretty good, right? Plus or minus 10% is unacceptable. Plus or minus 5% is unacceptable. Or is acceptable, I'm sorry. So just to give you an insight into how that works, virtually every Nobel Prize in physics has been given to somebody who couldn't calculate the value of their result better than plus or minus 5%. In some cases, we've given Nobel Prizes in physics to guys who couldn't calculate the number better than plus or minus 50%. Right? Seriously. A guy named Arno Penzias, he lives here, he's actually a venture capitalist now. Won the Nobel Prize, and the numbers he came up with were off by 50%. It was still a good number. Amazing. The margin of error is important because it gives you confidence in your data. That's all it's good for. It's not there for end users or anything like that. But when you're talking to your boss, right, and your boss is challenging you and saying, why do you have these outliers? Why is this slow? Is this data any good? I got a report from the VP in Singapore, and he said his page loaded really slow. I hear this a lot, right? Somebody called me and said our page was loaded really slow, right? Go fix it, right? You pop up the number and say, look, I took 1,000 data points over an hour in this area, and this is what my response time does, and I am 97% confident that that's what the real value is, regardless of what this individual outlier on the phone in the noodle shop or whatever it was, what his experience was. The experience for users in general looked just like this. And you can be very, very confident, surely through the law of large numbers, that that number is good. Just looking at it, 99% confidence interval, 95%, this is where we try to stay. Usually when I'm building a system, I just built a large performance management system for PayPal. I required that we get our numbers within the plus or minus 5%. The 90% N is the number of data points here. So this is just a quick set of easy formulas. You want to know how many data points you need to get to, the 99% confidence interval. Work it out. Solve for n, you'll know how many data points you need. And the numbers here actually are just working through the algebra for that. So once again, I'm belaboring the statistics, trying to get us to the point where we can talk about performance, but this background is really important. So last part of the statistics part, then we can take a break. The 5 number reports. Our first hands-on, we're going to do 5 number reports. We're going to go test Twitter. See how fast Twitter is. Then we're going to do a 5 number report, draw the distribution, see what the data looks like, and we're going to come up with some questions around that, like, why is it so slow? And where do these outliers come from? And why is my performance not reliable? All coming up. 5-number reports. This is just a simple way. You're given some set of data. Here's a jar of data points, Daniel. Now what are you going to do with it? The first thing I do is I run a 5-number report. This gives me a very vague idea of what the hell's happening with those numbers. Now I can talk sensibly about it. To create a 5-number report, obviously there's 5 numbers. I calculate the median, first and third quartiles, the minimum and the max. From this, I can get some really useful information. Shape of the distribution, extreme values, variance, skewness. Draw it. I'm serious. It's like I can't give you any better advice about mathematics, and I'm often asked, right? I can't give you any better advice about mathematics than just to draw it, right? Visually draw down the data points. So when we go to do a 5-number report, now of course in Excel you can sit there and go click and it'll just calculate the numbers for you. If you use R, there's a one-liner that calculates a 5-number report. I think it's actually just called 5num. It's on a slide coming up. Get used to doing 5-number reports. It's the quick and easy way to analyze your data. If you're lucky, you will never need to do any more statistics than this ever for your performance work. And you could probably get away with just knowing the 5-number report if you know what you're doing. So, a little bit of hands-on. Everybody have access to curl? Anybody not have access to curl? All right, so I will help you, and we will do it together on my machine. How's that? Before we do that, quick question. Do we want to have a break now, or do we want to do the hands-on and then take a break? Up to you.
How long is the hands-on?
You want to do the hands-on?
How long is the
Oh,
hands-on?
about 15 minutes.
Let's do the hands-on.
Let's do it? All right. So, curl. Curl's a text-based HTTP client. It's not a browser. It does nothing but dump nasty characters onto your screen. There's nothing to look at. It only works for a single object. It makes a single HTTP request, hauls whatever it is back, and splashes it on your screen. The curl is really, really, really valuable tool. I spend 10% of my life typing curl, I think. And I think I know every single option for it. And anybody who's typed man curl knows that that's pretty disgusting to know all those options, right? I mean, that's just pathetic. But it's really important. So for our test here, we're going to run 10 tests on Twitter using curl. We're going to gather 10 numbers for the response time. And then we're going to run a 5-number report, plot the results. And there's several goals I have. One is I just want you to get your hands dirty, measure some web pages, see what the numbers look like. Second one, get some experience running some basic statistics on this stuff. What can we learn just very quickly looking at the data? The curl command that you want to type in is the one here. Please type it in character for character. I didn't add or subtract any characters there, and they're all, This is Bill Joy talk that we're looking at here. He used to be my boss at one time, and I used to tease him mercilessly about how cryptic Unix commands are. But be that as it may, that's the command. Go ahead and type it in 10 times, collect the data. All right, don't just sit there and d. You want to write that number down or type it into your spreadsheet-like substance. At the end of it, you're going to have 10 numbers for response times. The numbers that curl produces, and I should point this out, are in seconds. So you'll get 0.251 or 0.14. You won't get 104. Right? It's in seconds, not milliseconds. You need to convert. All right, let me see what I can do for this gentleman. I know what I can do. All right. So I hope you're all gathering data and about ready to do your 5-number report. The next 2 slides kind of show people how to do that in Excel and in R. So I don't know which one you have. And so I figure most people are using Excel. These are the instructions for Excel. It's just very simple. And it's all just about this quartile min and max function. So quartile number 2, what is that? That's just the median, right? Remember our 5-number report, min, max, median, first and third quartile. Minimum, first quartile, median, third quartile, and max. So there's our 5-number report. So with this gentleman, we actually used curl on the iPhone. So we got numbers that are far, far greater and I can say that without ever having seen any of your data, right? The numbers that we got are far, far greater than the numbers that you guys are getting on your desktop machines. And we'll talk about why that is a lot today. Ladies and gentlemen, I'm going to move back to that previous slide just to look at that command line again. We've got a typo here. I'll come back to the Excel in a minute. And boy, I'm really happy to be able to stand up here in 2014 and say, ladies and gentlemen, when I first started giving these classes 2 years ago, it was gentlemen. There were no women. So I'm really happy to see. So can we learn anything by doing 10 tests? What do you think the margin of error is for 10 data samples? Going to be pretty large, right? Yeah, it's hard to do much reasoning on very limited samples. There's information there, but it's not necessarily very accurate. Okay, so let me just do a time check. Where are we? Does everybody gathered 10 data points? All right, anybody not still struggling to gather data points? Maybe the one fellow back here is still working on it, but I think everybody else is good. All right, so anybody having trouble just generating the 5-number report and the actual values?
Yeah, I got the syntax error around the second.
All right, hang on a second. I will come help you. So walking around and looking a little bit, it's kind of obvious that anytime somebody uses a tool for the first time, they have to struggle a little bit, right? Even if they're a really good tool user and even used to it, takes a little bit. The first time you do something, not going to come out right, might take a little time. Do you think that if you were going to do this in the future, let's say that tomorrow I come to you and say, okay, we're going to do Google, we're going to do Facebook, you think it'd be a lot faster for you to go through this process, gather the 10 numbers and just run the report, right? And the day after that, we're going to do it for, Amazon, right? And pretty soon you're going to be able to do this bing, 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 bing. And it won't take you much longer than it takes to actually do the measurements and gather the data to understand the distribution. And that's sort of the skill that I'm trying to get you guys to understand. I can't sit here and let's do this 10 times in a one-day class so that you can get used to it. What I want to do is put the tool in your hands and give you the opportunity to go and do these exercises a few times yourself, get some skill in it, make it an easy skill that you can go and whip out and say, okay, let's talk about Facebook's numbers. Bing, 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 there they are. Right? Let's talk about our website's numbers. Bing, bing, bing. There they are. Right? Looks terrible. Looks good. Whatever. Once you get the skill of doing this, it's a really, really fast way of doing the analysis. And so I'm really trying to get some skill development here rather than just, pontificating on as I normally do. And I have a tendency to want to lecture. My background is in mathematical physics. I'm only comfortable with something in my hand doing this, right? So I really made an effort to get some more hands-on into these classes this year. And this was one of the ways that I wanted to do this, was to try and build some of these basic skills. Sure. Let me just flip back to the Excel slide here. Oops. I don't expect you guys to memorize these commands sitting here on a PowerPoint slide. What will really happen is you'll do it a few times and it'll just be obvious to you. Or you'll set up a formula to just make it happen in Excel. That's what I did. But pretty straightforward. I'm going to give us maybe another 2 or 3 minutes, and then I'm going to pick somebody and we're going to look at their numbers and we're going to plot it. Like I said, draw it. I may need a marker. No wonder I feel so uncomfortable today. No marker. No, I'm just teasing. All right, we'll wait for this gentleman to come back with the marker. Anybody still having problems with generating the report? That was easy, huh? Yeah. And now you know quite a bit about that distribution. So extra credit while we're waiting, plot it for yourself. You don't have to wait for me to do it. Get a piece of paper, draw your axes, and go for it. Getting your hands on the data, personal knowledge. All of science, all of engineering involves an element of personal knowledge, of putting your hands on something and understanding it, right? We like to think, oh, science, very formal, very dry. You can go into any lab and reproduce this experiment and that one. Doesn't happen. What really happens, there's an element of personal knowledge that goes into it, of skill, ability, and experience. In web performance science, exactly the same way. If you're going to be a performance expert or even speak knowledgeably about this, you really want to get that personal, hands-on, intuitive feel for what the numbers do. Plotting things by hand helps you develop that personal knowledge, that intuition that's important for a real scientist. First quartile?
First quartile, 0.05575.
Okay.
The second one.
It's the median.
Sorry. Median, 0.0685.
All right. The
Q3, 0.164.
all right. And the min and the max.
The min is 0.043.
And the max.
0.522.
All right. So these are the numbers that this guy got for Twitter. And the first thing that you can see is that for 10 measurements, the range is pretty wide, right? The difference between the min and the max is over an order of magnitude, right? So now you know you've got a pretty highly variable data set, right? And all you had to do was look at the min and the max. You don't even care about the quartiles to make an important observation. This is not very clean data, right? Not very tight distribution. What else can we learn from this? And remember, we haven't plotted it yet, right? So the median, it looks like, if I look at the values of the min and the max, and this is about half, right? 0.52, and this is about 1/20th, right? 5%, right? So I got 5% and 50%, just roughly, I'm just sort of approximating. And I look at the median is 6%. It's very close to the minimum value, right? Much closer to the minimum value of the distribution than it is to the max. What does that tell me? Now, the median means that half the data is on this side and half the data is on that, right? So just by definition, without looking at any of these other quartiles, I know right away that half the data set lies between 0.05 and 0.06, right? Just by looking at the median and the min and the max. And I know for a fact that that's a pretty lopsided distribution, right? Half the data set is in this one little segment, and the rest of the data set is in this huge long tail, right? So this is what I can learn just gazing at it. And I haven't even looked at the individual quartiles here, but they're just supporting information. The first quartile and the mean, not radically different, right? The third quartile, a little bit different, but still not very close to the max. All three of those numbers, Q1, Q2, and Q3, are very, very close to the left edge of the distribution, farther from the right. So without ever drawing it, I already know a lot about this distribution, and just from what I just said, I can actually just draw it, no problem, right? So what does it look like? So let's say 1, 2, 3, 4. So if I want to plot the first quartile, let's just try something like this. See, this is our problem right away. So this distribution goes something like 0.05 is our minimum. And we're just going to accept that and take the first quartile, 0.55, so it's about right there. The median is 0.68, so it's not very different. Third quartile, if this is 0.5 and this is 0.05, then 16 is right there. And then the max is at 55, which is right here. So this distribution looks like that. But we knew that already, right? Am I right? Okay, guys, what did I say earlier about does it seem reasonable or not? Does that seem reasonable? Is that what you thought that distribution looked like? Guys, we just said more than half the data set lies between 0.05 and 0.06, right? I mean, somewhere here, right? So I drew this incorrectly because I wanted to, A, see if you were listening, but B, also show you how obvious it is to determine what's reasonable and what's not, right? We know what this distribution looks like. Closer to something like that, right? We know that, and I purposely did not draw the axes here because I wanted you to think about if you could do this qualitatively. We know that the median, let's say that this is the median, right? We know that's about, what was it, 0.16? No, 0.06. Right, so we know half the data points are over here, and half the data points are over there, right? And we know that the range goes all the way out to 0.522, I think was that, right? So we know that this distance is a hell of a lot more than this distance, right? So this is what our curve looks like. Just qualitatively, we knew that that was kind of what it looked like. Most performance curves look pretty much like this, right? There's not a lot of data over here where things are really fast, right? Because you can only make them so fast and 0 isn't an option, right? That's only with interest rates, right? We know that there's usually some long tail, and if we know the median, then that's going to be the shape of our curve, right? What I really want you to do here is get the habit and the skill of thinking through the data, looking at it, and being able to just whip and draw that out, right? What if it was a different data set? What if it looked like and had multiple peaks along here? What would you think about that? I mean, you're not going to really get that with 10 data points. It's hard, right? But you'll see distributions like this. What are you going to do about that, right? You're going to start looking for causes. 1, 2, right? Different distributions, right? Drawing this stuff out gives you some immediate insight into what's going on. If you see this, you're like, that's pretty reasonably close to what I've seen on other websites. It's not radically dissimilar, you know, it's like, unless the numbers are really radically off in magnitude, it's probably okay, right? Probably not too broken, right? You see something like this and you're like, highly variable, multiple peaks, right? It's like, oh, there's something wrong there. Right? Immediately, you ran the 5-number report, you ran your test, you ran the 5-number report, you drew it, you immediately found a problem. If you gain some experience, you might even guess what the problem was. If you see a multi-peak distribution here, what you're almost certainly seeing is performance distributions globally, where these folks are somewhere in Europe and these folks are somewhere in Asia, right? And you're just seeing global distributions. But that comes with experience. Right? Getting the experience of hands-on handling these numbers. What do performance data really look like? So hey, let me just ask 1 or 2 more questions before we go on the break. So I worked with you on the mobile device. So don't hold up your hand because your data is going to be your response times are a lot larger than the rest of ours for the moment. Anybody have a number greater than, what was the max back here? 0.164. Anybody have a max greater than about 0.16?
522.
Give me 577.
577. Okay, so anybody get a minimum less than about 0.05? What'd you get?
0.047.
31.
4. I got 0.04.
Okay, so it sounds like our range across roughly, there's 30 people in here, so we did about 300 measurements, right? And our range across that data set is like from 0.034, I think was the minimum, to this gentleman had, 500 milliseconds, right? So that's a pretty wide range. but we're all sitting in the same room, we're on the same network connection, going to the same URL at roughly the same time of day. Why is it so variable? I mean, can you think of other cases where I could go measure something 10 times in a row real fast and the numbers come out radically different with a huge range like that? All right, it's time for a break. Let's go take a break. It's exactly 10:30 and we finished that. I hope that you learned something about response times. They're highly variable and they're all over the map and they're not tightly clustered, right? The second thing that you might learn is that you can see very large outliers toward the right, right? Sometimes we see very long response times that don't really correspond to either the median or the mean. The third thing that you might have learned is that when you go through and test this data, you can't really count on getting really tight results, right? Even if you're sitting there doing the same test over and over again. The internet itself is subject to stochastic fluctuation, and what that means is nobody has a clue. That's exactly what stochastic means, right? We say random variation, but random just means we don't have a clue. Nothing out there is really random, right? The internet fluctuates, the wind blows, response times go down, wind blows, response times go up. Anybody that sat and watched, so who here has actually used a BitTorrent client? Right? Okay, come on, you don't have... It's like, come on, I know the story, guys. More seriously, when you look at the BitTorrent client, so there's a couple BitTorrent clients that actually show you the download speeds, right, of what's happening out there on the network. And you see the wind blows and the response times all go down to 0. And then the wind blows and it all goes back up. And there's actual winds, performance fluctuations that are periodic out there on the internet. We can measure these long-term standing performance waves. That's not the subject for this class, which is getting started. But there are really long-term standing response time waves in the actual structure, which just blew my mind when I first encountered it. I'm like, you gotta be kidding. I didn't read that book. Anyway, break time. 15 minutes.